Okay, hello everyone, in a new video in part 6 of chapter 10, which is the chapter of Archimedes upthrust in the third unit of mechanics. So in this part we are going to complete solving exercises. Then we have reached exercise number 12. Is it easier to swim in the fresh water of a lake or in seawater? So the opening of this exercise is a question. To answer this question, we perform the two following experiments with a solid S of mass m is equal to 2 kilograms. So the given solid has a mass m is equal to 2 kilograms. Given that g is equal to 10 newtons per kilograms, which means that we are performing this experiment on the surface of Earth. So number 1, first experiment. S floats at the surface of the water of the lake of density 1000 kilogram per meter cube. So here S is floating at the surface of water, which means it is at equilibrium. So 1.1. So this is the density of the water of the lake. So let's write here that the density of the lake is equal to 1000 kilogram per meter cube. 1.1, what condition must the two forces acting on S satisfy so that it floats at the surface of water? So in other words, they are asking me about the condition of equilibrium. So let's write at equilibrium. Then how do you apply this condition? Always on the left we write the sum of forces acting on the solid S. So what are the forces acting on the solid S? Because it has a mass, then it will be directly subjected to the weight vector W. And because we have a liquid, and in particular the lake, the water of the lake, then it will be directly subjected to the Archimedes upthrust. Then the forces are given by weight plus F upthrust. And on the other side of this equation, we write the zero vector corresponding for the condition of equilibrium. Then W vector moving F upthrust to the right hand side, then W vector is given minus F upthrust. So what does the first equation tells us? That the effect of both forces acting on the solid S cancel each other. So this is the first equation. Whereas the second equation tells us that both forces have the same line of action, opposite direction, and same magnitude. Now in 1.2, calculate the value of the weight of S. So knowing the mass and knowing g, and here by the value they mean the magnitude, then the magnitude of the weight is given by m multiplied by g. No need to construct a triangle because this is the quantity that we want. Then the value of m is given by 2, the value of g is given by 10, so the value of the weight is given by 20. Since everything in the SI, so the value of W will be in the SI, which is in newtons. Then the weight of this object is given by 20 newtons. And here, let me say the following note. Since we have a liquid, then we must distinguish between two types of weights, and they are given by the real weight and the apparent weight. So we have the real weight and the apparent weight. But at the level of the forces, whenever we consider the weight, so we will be talking about the real weight and not the apparent weight, okay? And here the magnitude of W, this represents the magnitude of the real weight vector W. Now in the same part they are telling me to deduce the value of Archimedes upthrust, and by deduce it means that we need to use the part just previously before. In this part we have determined the value of the weight, and knowing that weight vector is equal to minus F upthrust given by the condition of equilibrium. So we are interested in determining the value of Archimedes upthrust, so in other words the magnitude of F. We are interested in the magnitude of this relation, so let's say in magnitude. Then what we will do here is we'll drop the vectors and remove the minus sign. So W is equal to F upthrust. But we know that the value of W is given by 20 newtons. Then the value of F upthrust is given by 20 newtons. So in this case, F upthrust is given by 20 newtons. Now in number 1.3, so let me do 1.3 here. Calculate the volume V1 of the immersed part of S. So we know that the immersed volume, which is denoted here in V1, and the magnitude of F are related via the following formula, that F upthrust is equal to the density of the liquid times the volume of the immersed part times G. We are interested in determining Vi. So constructing the triangle of this formula, here because we have multiplied and F upthrust will be at the top, rho L, Vi and G at the bottom, we are interested in determining Vi, which is denoted by V1. Then V1 is given by the magnitude of F upthrust, which is denoted by F upthrust, divided by the density of the liquid, and here the liquid is given by the water of the lake, which is denoted by rho lake, multiplied by the value of G. The value of F upthrust is given by 20, and the density of the lake is given by 1000, multiplied by 10. Plugging this fraction on the calculator, then the volume of the immersed part is given by V1 is equal to 2 times 10 to the power minus 3. Since everything in the SI, so the volume V1 will be expressed in the SI, which is meter cube. So the volume of the immersed part when the solid S is immersed in the lake is given by 2 times 10 to the power minus 3 meter cube. So let me write here that V1 is given by 2 times 10 to the power minus 3 meter cube. Now in the second experiment they are telling me that S floats at the surface of seawater of density 1040 kilogram per meter cube. So here, because S is floating at the surface, then we can use also the condition of equilibrium. So the density of seawater is given by 1040 kilogram per meter cube. So the density of the sea is given by 1040 kilogram per meter cube. Let me make some space here. So knowing that the magnitude of W here is given by 20 newtons. So we are in a second experiment and part 2.1. They are telling me that the Archimedes upthrust remains the same. Why? So here, because the solid S remains at equilibrium, although the liquid has changed from the water of the lake to the seawater, however, the solid S remains at equilibrium. So let's say that S is at equilibrium. So what do we mean by that S remained at equilibrium? So between brackets, that the magnitude of W is equal to F upthrust. So recall that we have determined this relation from the condition of equilibrium, which is given by that the W vector is equal to minus F upthrust. And in this case, and the magnitude W didn't change. So why the magnitude W didn't change? Because simply we didn't change the solid S, so the mass remained the same. So in this case, if the following equation also holds and we didn't change the value of W, so the value of F upthrust didn't change as well, then the magnitude of Archimedes upthrust remains the same. So notice that in part 2.1 they are asking me about Archimedes upthrust remains the same and not the magnitude. But it's obvious that they are asking me about the magnitude, because we know that for the line of action and the direction of Archimedes upthrust, they will never change. So F upthrust always act vertically upward. So in this case, F upthrust is also given by 20 newtons, which is the value of the weight. Now in part 2.2, Calculate the volume V2 of the immersed part of S. We know that the value of F and the immersed volume are related via the following formula, that F upthrust is equal to the density of the liquid times the volume of the immersed part times G. We are interested in determining Vi. So constructing the triangle of this formula, here because we have multiplied, then F upthrust will be at the top, rho L, Vi and G at the bottom, knowing that we are interested in determining Vi, which is denoted by V2, and it's given by the value of F upthrust divided by the density of the liquid. Notice that here the liquid is given by the seawater, and the density of the seawater changed from, so previously the liquid was given by the water of the lake, which and its density is given by 1000. Now in this case the liquid is given by the seawater and its density is given by 1040 kilogram per meter cube in the SI. So here the density of the liquid is represented by the density of seawater multiplied by the value of G. Then the value of F upthrust is given by 20, and the density of seawater is given by 1040 multiplied by the value of G, which is 10. Now plugging this fraction on the calculator, then the value of V2 is given by 1.92 times 10 to the power minus 3. Since everything is expressed in the SI, so volume V2 will be expressed in the SI, which is meter cube. Then the volume V2 is given by 1.92 times 10 to the power minus 3 meter cube. And let me write here that the volume V2 is given by 1.92 times 10 to the power minus 3 meter cube. Number 3. Answer for the question. Knowing that swimming is easier when the immersed volume of the floating object decreases. So what does this mean? When comparing immersed volumes together, the smallest volume makes swimming on this liquid easier. So is it easier to swim in the fresh water of a lake or in the seawater? So we need to check whether the swimming is easier in the fresh water of a lake or in the seawater. And this can be done by comparing the immersed volumes regarding the water of the lake and the seawater. So let's compare the immersed volumes in each case, and they are given by V1 and V2. So knowing that V1 is given by 2 times 10 to the power minus 3 meter cube, and V2 is equal to 1.92 times 10 to the power minus 3 meter cube. So by compare, we mean that we need to say whether V1 is less, greater or equal to V2, and in this case V1 is greater than V2. And here they are telling me swimming is easier when the immersed volume is smaller, which is decreases. So in this case, swimming, so V2 is less than V1, and V2 represents the immersed volume when the solid S is immersed in the seawater, which means that swimming in the seawater is easier. Then let's say since the immersed volume of the seawater is less than, so here the immersed volume of what? Of the object S is less than the immersed volume of the water of the lake, which means that swimming in seawater is easier. And now let's move to the next exercise. Exercise number 13. An iceberg is a huge block of ice that floats on the surface of water. In order to show the danger of icebergs in marine navigation, we take a piece of ice of mass 0.135 kilograms. So let's denote this mass to be m is equal to 0.135 kilograms. And of volume V is equal to 1.5 times 10 to the power minus 4 meter cube. So what does this volume represent? It represents the total volume of this piece of ice and a container with a sufficient amount of water of density 1000 kilogram per meter cube. So let's denote the density of water to be given by raw water 1000 kilogram per meter cube. Take G is equal to 10 newtons per kilogram, which means that we are performing this experiment on the surface of Earth. Now, we immerse the piece of ice completely in water. So it's completely immersed, which means that the immersed volume is equal to the total volume of the of the piece of ice. Now, and we release it. 1.1, name the two forces acting on the piece of ice and water. So here let me do a small sketch. This is the container containing water. And this is the piece of ice. This is water. Now 1.1, name the two forces acting on the piece of ice and water. So because this piece of ice has a mass, then it will be directly subjected to the weight which is vertical downward. So one of the forces is the weight W. And here, because we have a liquid which is water, then the piece of ice will be directly subjected to the Archimedes upthrust force, which acts vertically upward like this. And the other force is given by Archimedes upthrust force, F upthrust. Now 1.2, give the line of action and the direction of each of the two forces. So let's start by the weight W. They are not asking me about all the properties, they are just asking me about the line of action and the direction. And we need to list them in this order, the line of action, then the direction, according to the building. So the line of action is given by vertical. And the direction is given by downward. Whereas for the Archimedes upthrust, the line of action is also given to be vertical, and the direction is given by upward in this case. Now in 1.3, determine the value of each force, and by the value they mean the magnitude. So because we know the mass of this piece of ice and we know G, then we can directly determine the weight. And here let me say the following: by this weight vector we mean the real weight and not the apparent weight. So we must distinguish between the real weight and the apparent weight, because whenever we have a liquid we can talk about the apparent weight, but whenever we are discussing forces, this weight represents the real weight, and its magnitude is given by W is equal to M multiplied by G. So the value of M is given by 0.135, and the value of G in the SI is given by 10. So plugging this on the calculator, then the value of the weight is given 1.35. Since everything is expressed in the SI, so the value of W will be expressed in the SI, which is in newtons. So the value of the weight is given by 1.35 in newtons. And now we need to determine the value of the other force, because they are telling me determine the value of each force, and the forces are given by the weight and the value of F upthrust. Now the first thing that comes to our mind is that to determine the value of F upthrust using the condition of equilibrium, but notice that till this moment they didn't mention anything about the condition of equilibrium, so we are not allowed to use it. And simply because here they are telling us we immerse the piece of ice completely in water and we release it. So when we have placed ice in this position, we don't know whether ice will float to the surface or sink to the bottom or float inside the liquid. So yet the piece of ice is not at equilibrium. Then we cannot use the condition of equilibrium, which is given by W vector plus F upthrust is equal to 0 vector, because yet this condition doesn't hold. So we need to find another method to calculate the value of F upthrust, knowing that we have the density of water and we know the value of G, and because as the piece of ice is completely immersed in liquid, so the immersed volume is equal to the total volume, then we can calculate F upthrust using its definition, which is given by the density of the liquid multiplied by the volume of the immersed part multiplied by G. No need to construct a triangle for this formula because this is the quantity that we want. Here in this case, the volume, since the piece of ice is totally immersed in the liquid, then we have that VI, the immersed volume, is equal to V. Now let's rewrite the expression of F, replacing VI by V. So F upthrust, which is noted by F upthrust, is equal to the density of the liquid, which is given by water, so rho of water, multiplied by the total volume of the object, multiplied by G. Now the density of water is given by 1000. The volume V is given by 1.5 times 10 to the power minus 4. And the value of G is given by 10. Now plugging this expression on the calculator, then the value of F upthrust is given by 1.5. Since everything is expressed in the SI, so the value of F upthrust will be expressed in the SI, which is in newtons. So F upthrust is given by 1.5 in newtons. So here let me write that the value of the weight is given by 1.35 in newtons and the value of F upthrust is given by 1.5 in newtons. Now we are in part 1.4. They are telling me the piece of ice starts rising in water. Why? So notice that the magnitude of W is given by 1.35 in newtons, whereas the magnitude of F upthrust is given by 1.5 in newtons, knowing that the weight vector W is acting vertically downward and the F upthrust is acting vertically upward. So comparing the magnitude of these two forces, we can notice that F upthrust is greater than the value of W. So the action of F is greater than W. For this reason, the piece of ice starts to rise. So let's say, or first let's compare the magnitudes, which is given by, so W is given by 1.35 in newtons, and the value of F upthrust is given by 1.5 in newtons, which means that F upthrust is greater than W. And let's say since the magnitude of F upthrust is greater than that of W, so then that of W by, it means that the magnitude of W. For this reason, then the piece of ice starts to rise. Now in number 2, the piece of ice floats in equilibrium on the surface of water. In this case we can use the condition of equilibrium, and indeed in part 2.1 give the condition of equilibrium of the piece of ice. So how do you apply this condition? Always as a title we write at equilibrium. On the left we'll always write the sum of forces acting on the solid S, and they are given by the weight and F upthrust. And on the other side of this equation, we write the zero vector corresponding for the equilibrium, and we don't forget the vectors on these three quantities. Now moving F upthrust to the right hand side, we have that W vector is equal to minus F upthrust vector. So what does the first equation tells us? That both the effect of both forces acting on the solid as cancel each other, whereas the second equation tells us that both forces have the same line of action, opposite direction, and same magnitude. Now in 2.2, determine the volume V1 of the immersed part of the piece of ice. Now we are in part 2.2. So we need to determine the volume of the immersed part. So the immersed part always appear in the following equation: F upthrust is equal to the density of the liquid times the volume Vi times G. So in order to determine the volume of the immersed part, we must know the density of the liquid, which is given, density of water. We must know the value of G, which is given 10 Newton per kilogram, and the value of F upthrust as well. So here we cannot use the value of F upthrust, which is given by 1.5 newtons, and this is because simply now the solid S is at equilibrium, and the value of F upthrust change, so it will change from 1.5 newtons to the value of W, which is given by 1.35 newtons. Okay, so here let's use the condition of equilibrium to determine the new value of F upthrust, because now F upthrust is at equilibrium, whereas when the solid S was completely in water and it was released, the value of F upthrust was determined from the following formula: rho L times Vi times G, and we have used the fact that Vi is the total volume of the solid S. But now, because the solid S is floating on the surface like this, the volume of Vi changed, and it's no more equal to the total volume of the piece of ice. Now, so for this reason, first let's determine the new value of F upthrust, which is given by the condition of equilibrium. So W vector is equal to minus F upthrust vector, and notice that the value of the real weight will not change because it depends on the mass, and the mass didn't change as well. So in magnitude, we have that W is equal to F upthrust, but the value of W is given by 1.35 newtons. Then the value of F upthrust is given by 1.35 newtons. Then the value of F upthrust is given by 1.35 newtons. And now we are ready to calculate the volume of the immersed part, which is denoted by V1, corresponding for this value of F upthrust. So knowing that the immersed volume appears in the following equation: F upthrust is given by the density of the liquid times the volume of the immersed part times G. We are interested in determining the volume Vi. So constructing the triangle of this formula, here because we have multiplied, and F upthrust will be at the top, rho L, Vi and G at the bottom. We are interested in determining Vi, which is denoted by V1, which is given by F upthrust divided by the density of the liquid, which is denoted by rho W, multiplied by G. The new value of F upthrust is given by 1.35, divided by the density of water, which is given by 1000, multiplied by G. So the volume of the immersed part after plugging this fraction on the calculator is given by 1.35 times 10 to the power minus 4. Since everything is expressed in the SI, so the volume V1 will be in the SI, which is meter cube. So the volume V1 is given by 1.35 times 10 to the power minus 4 meter cube. Now in 2.3, calculate the ratio V1 divided by V. The value of V1 is given by 1.35 times 10 to the power minus 4 meter cube. And the volume V is given by 1.5 times 10 to the power minus 4 meter cube. Now, plugging this fraction on the calculator, then the ratio V1 divided by V is given by 0.9. So therefore V1 divided by V is given by 0.9. So notice that for this ratio I didn't include any unit, because for this simple reason that meter cube goes out with meter cube. So here it is meter cube. So as we stressed earlier that all quantities in physics must include a unit, but it happens sometimes that some quantities doesn't include a unit. For example, when we are filling quantities in a table and the unit is included in the first column. This is another example where numbers doesn't include any unit. So usually in physics, whenever we are dividing or we are calculating ratios of same quantities, then this ratio doesn't include any unit. So for example, if we have written here that V1 over V is equal to 0.9 meter cube, then this answer is considered to be wrong, because we know that the ratios of the same quantities don't have any unit. So the ratio is given V1 divided by V is equal to 0.9. Now in 2.4, the ratio V1 divided by V shows an evidence of the danger of icebergs. Explain why. So we need to deduce from this ratio why icebergs are considered as a danger in marine navigation. Okay, so knowing that V1 divided by V is equal to 0.9, so here 0.9 is not divided by anything, so it's considered to be divided by 1. Let me write on a new line that V1 divided by V is equal to 0.9. It means that it is divided by 1. Now if we cross multiply, so V1 multiplied by 1 is equal to 0.9 multiplied by V, which means that V1 is equal to 0.9 V. Now notice that 0.9 can be written as the following fraction: 90 divided by 100. So why 90 divided by 100 and not 9 divided by 10? Because we are interested in percentage or proportionality. So V1 is equal to 90 divided by 100 multiplied by V, which means that V1 represents 90% of V. So what does V1 represent and what does V represent? Or in other words, what does this statement means? So suppose that this is, okay, now let's consider when the piece of ice is floating on the surface of this water. So this is V1 and this is V, the total volume V. Okay, and this is the volume of the emergent part. Here what we are saying is that V1 represents 90% of V, which means that the majority of the volume is found inside the water. So for this reason, icebergs are considered as a danger, because the majority of the volume is found inside the water, which is given by 90%. So if we see an iceberg floating on the surface of water, so although the floating part of this iceberg is very small, which is considered to be in this case 10%, because 10 plus 90 is 100, but this doesn't mean that the other part, which is inside the water immersed in the liquid, is considered to be small, because it represents 90% of the total volume. So here let's say, so I will continue this part here. For this reason, okay, the majority of the volume is inside the liquid or is immersed in the water. For this reason, icebergs are considered to be dangerous. And now let's move to the final exercise, which is exercise number 14. In an experiment, we use an egg of mass m is equal to 55 grams. So knowing that the grams is not the SI unit of mass, in order to convert from grams to kilograms, we divide by 1000. Then 55 divided by 1000, then the mass is given by 0.055 kilograms. And a graduated cylinder containing 200 centimeter cube of salty water of density rho salty is given by 1200 kilogram per meter cube. So knowing that the density of water is usually given by 1000 kilogram per meter cube, because of the presence of salt in this water, then the density is larger and it's given by 1200. We immerse the egg completely in the salty water. The level of the salty water rises till 250 centimeter cube, as shown in the below document 1. Then they mentioned this document, now we can use it. So before we immerse the egg, the volume of this water is given by 200 centimeter cube, so this is V1. And let's say that the volume V1 is given by 200 centimeter cube. Knowing that centimeter cube is not the SI unit of volume, in order to convert from centimeter cube to meter cube, we multiply by 10 to the power minus 6. Then 200 multiplied by 10 to the power minus 6. Then the volume V1 is given by 0.2 times 10 to the power minus 3 meter cube in the SI. And the volume V2 after we immerse the egg is given by V2 is 250 centimeter cube. Knowing that centimeter cube is not the SI unit of volume, in order to convert from centimeter cube to meter cube, we multiply by 10 to the power minus 6. Then the volume V2 after we immerse the egg is given by 0.25 times 10 to the power minus 3 meter cube. Now number 1, calculate the magnitude W of the weight of the egg. So here, because we have liquid, we must distinguish between the apparent weight or the real weight. Since they didn't mention whether this weight is the real weight or the apparent weight, so we take it as a default to be the real weight, which is given by m multiplied by g. The value of m is given by 0.055 multiplied by the value of g, which is 10. Then the magnitude of the weight is given by 0.55 in newtons. So the magnitude of the weight is given by 0.55 in newtons. Now in number 2, calculate the volume of the egg. So here the egg is not considered to be as a regular shape, so we cannot calculate its volume using a formula. However, here, because we have the two volumes, volume V1 and V2, then we can calculate the volume using water displacement, which is given by the difference between V2 minus V1. So the volume V2 is given by 0.25 times 10 to the power minus 3, and the volume V1 is given by 0.2 times 10 to the power minus 3. Then the volume V will be given by, after we plug this on the calculator, is given by 0.05 times 10 to the power minus 3. Since both volumes are expressed in meter cube, then the volume V will be expressed in meter cube. So the volume V is given by 0.05 times 10 to the power minus 3 meter cube. So we can also write that V is given by, so let me erase this. So actually, if we plug this on the calculator, the volume V is given by 5 times 10 to the power minus 5 in a more compact notation using the power. So I have included the two zeros inside the power. Now in number 3, calculate the magnitude F of the Archimedes upthrust exerted by the salty water on the egg being completely immersed in the salty water. So this gives us a hint that we must use that the immersed volume is equal to the total volume of the egg, which is given by, in this case, 5 times 10 to the power minus 5. So the value of F upthrust, which is denoted by F, is given by the density of the liquid, which is denoted by the density of salty, multiplied by the volume. So let's say the density of the liquid times the volume of the immersed part times G. No need to construct a triangle because this is the quantity that we want to determine. But here the immersed volume is equal to the total volume because it's completely immersed. So let's say since the egg is completely immersed in the liquid, then in this case Vi is equal to V, and let's rewrite the expression of F replacing Vi by V. So the value of F, which is denoted by F, is equal to the density of the liquid, which is denoted by rho salty, multiplied by the volume of the immersed part, which is V, multiplied by the value of G. Now rho salty is given by 1200, and the total volume is given by 5 times 10 to the power minus 5, and the value of G is given by 10. Plugging this on the calculator, then the value of F is given by 0.6. Since everything is expressed in the SI, so the value of F is expressed in the SI, which is in newtons. So F is equal to 0.6 in newtons. Then here, let me write that the value of the weight is given by 0.55 in newtons, and the value of F is given by 0.6 in newtons. Now number 4, we release the egg. Specify whether the egg rises to the surface of the salty water or falls to the bottom of the cylinder. And here by specify, for sure it means we need to justify. So what are the forces acting on the egg? We know that we have the weight which is acting vertically downward on the center of gravity of the egg, and F upthrust, which acts also on the egg on the center of gravity of the immersed part. Since the immersed part is the total volume, so F will also act on this point vertically upward. And the rising or the sinking of the egg depends on the magnitude of the forces. So we know that the value of W is given by 0.55 in newtons, and F is given by 0.6 in newtons. So knowing that F upthrust acts vertically upward and the weight acts vertically downward, and in magnitude the value of F is greater than W, which means that the action of F is greater than W. For this reason the egg will rise to the surface of the water. So first let's justify using comparison that the value of F is given by 0.6 in newtons, whereas the value of W is given by 0.55 in newtons. And by comparison it means we need to mention whether F is greater, larger or smaller. So in this case F is greater than W. Now since the magnitude of F is greater than that of W, for this reason the egg rises to the surface. Of salty water. And by this we have finished solving this exercise. So that's it for me in this video, guys. In the next part we'll complete solving exercises on this chapter.